So if I tell you if I have a beam that is quite deep, made of concrete, this is the engineering notation for concrete. So this is a beam, 6 meters long, made of concrete, and the total weight is 600,000 Newton. And if I tell you that the weight is here, so is it reasonable to say that this beam, that this load, that this force is just a single force concentrated in the middle? Let me give you another example. If it's the same beam and you have a chandelier that weighs like 600 Newton, are these two situations the same? No. The weight is not concentrated in one point. The weight of the chandelier could be, and that makes a lot of sense, just one line. And so a more accurate representation of this would be to say no. The weight is actually several smaller weights that's everywhere, okay? It's not just a single weight. And if you want, you can say this is 100 Newton for every millimeter. Because every millimeter of this beam is carrying part of the load. Okay? So I divided 600,000 by 6,000 millimeters. Then I managed to calculate that there are 100 Newtons per millimeter. That's more accurate. Okay? I could make my life a little bit easier and say, okay, I could represent it as 100 kilonewton per meter. So that transfers to you that what I have is actually a distributed load, not a concentrated load. Okay? This is more accurate. Okay? For the time being, when you are calculating the reaction, it doesn't matter. So if I give you this, you can say, yeah, it is this. If I give you this, you can say it is this. In November, we will discover that in few cases and in few issues, it matters. Okay? So today I'm introducing two things, what is called the distributed load, and the other thing is, for calculating reaction, there is no difference. Okay? But you have to keep in the back of your mind that in November, we'll see another difference. Okay? Let's see, where do we see this distributed load elsewhere? Okay, as I showed you in the weight, let's assume that you have a bookshelf and you decided to put the big books here and then smaller books here and then the tiny books here. Okay, and you calculated the weights to be 2 Newton for every meter, 3 Newton for every meter, 4 Newton for every meter. And this is 2, 2, 1, 2. How would I represent this as a free body diagram? That's very easy. And so this would be my free body diagram. Part of the shelf doesn't have anything. Part is suffering a little bit more and more. Okay, where are these forces? Like, if I want to calculate the reaction, I shouldn't use this. I should use the combination of them. So this is if I am calculating the reaction, this is what I would do. I'll say 2 Newton per meter for 2 meters, that is 4 Newtons, and I'll put it here. Three Newtons per meter for 1 meter, that is 3, and I'll put it here. And then 4 Newtons per meter for 2 meters, that is 8, and I'll put it here. Okay? Now, notice I said like every distributed load by itself. That would make my life easy, okay? One of you could be smart and say, you know what? Every load that you calculate is basically the area under the curve. So you said 2 by 2. So this is 2, and this is 2. I got the area and said it's 4. 3 by 2 by 1 is 3. 4 by 2 is 8. Someone could say, you know what? I could have found this whole area and got the total load. And the total load is actually 15. But where is this total load? You don't know. This total load is at the centroid of this shape. And so far, we have not studied the centroid. So I don't know where it is. So I don't go into that area, and I take each one of them by itself. Okay? Let's look at another beam. This is a roof of a building. And here is news to those of you who are new to Canada. In the winter, the roof carries snow. And it's not equal all over. Like you'll find more here and less here. Okay, so we will represent this way. So the load is distributed, but not a rectangle. It is a triangle. And if you manage to calculate that it is 10 Newton per meter here, I can replace this. If I'm only calculating the reaction, and I'm not doing the other thing in November, which is called bending moment diagram, I can just replace it with one force. And this force is going to be here in the middle? No. Where is it going to be? Yes. It's 1/3 from the base where the centroid of a triangle is. So this is the centroid of a triangle. This is where the force is going to be. And so this distance here is 2/3 of a 5. And this is 1/3 of a 5. How much is it? It's the area under the curve, which is 10 by 5 over 2. It's 25 newtons. Did I see a hand?
So what's the centroid and how do we know where to find it?
That's a very good question. We will have a full day, one lecture to teach you this in November. But the whole idea is if you have something like this, this is the center of the weight. If you have something like this, this is the center of the weight. If you have something like this, this is the center of the weight. If you have something like this, this is the center of the weight. And here is the kicker. If you have something like this, it's not in the middle. It is 1/3 from the base. So this is 1/3, and this is 1/3. And we start with this. It's a given. If you want to study it on your own, you can do calculus and you'll find it easily. Now, the kicker in all of this is this. What if you have a load that is like this? And let me show you an example of this. Some of you have heard about the typhoon that hit the Philippines and the hurricane that hit the Carolinas. Well, here's a tall building. The wind speed at the bottom is almost nothing because it's just next to earth and there is not much of flow. But at the top, it's high. So this is kind of the wind speed acting on the building, this tall building. And because the wind is strong, it's actually considered a load. There are engineers who just study the speed of the wind and how much does it impact buildings. I'm sure some of you seen, I guess in the Philippine typhoon, some buildings doing it like this. And that's because of the wind force. How do we represent this wind force? We represent it this way. So officially, if you want to really find the exact force, you need to find the area under the curve. And that will be calculus. And then find the centroid of this and put it where the centroid is. But for the time being, we simplify this by saying, you know what? We will use this. It's a little bit safe because we are more here. And so we'll say this is like 5 Newton per meter. I guess it's 5 kilonewton per meter then. And it goes to 0. OK, let's assume that you have here 20 meters and here 30 meters. So the load that I have is the total area under this curve, under this trapezoid, and it's at the centroid of the trapezoid. But I don't know where is the centroid of the trapezoid. I divide it into 2 forces, one here and one here. This force will be in the middle of the 20, so that means it's 40. And this force will be at 2/3 of the 30, it will be at 20. And I'll say 5 by 20 is 100. 5 by 30 over 2, which is the area, that's 75. And then I design my building this way. There is a system whereby you see the building as this. And that becomes the load on the building. If you're smart, you do something like this. And this is why you see some buildings doing like this. Those of you who are going through University Avenue, they are doing this. And this kind of triangular shape is called truss, which would be in 2 weeks. So let's take an example. It's a very straightforward thing, so I want you to study it more from the book. We'll give you one example. And if it's not easy, then tomorrow I can give you more. So this is a fixation, a shelf or a balcony that's coming out of a building. So the first thing is I get rid of the distributed load because I'm only required to find the reactions. And so I have the concentrated load, nothing happens to that. I have the distributed load, and instead of it being distributed over 4 meters, I just get the area under this curve, which is 5 by 4, that's 20. And this becomes Newton, and this is Newton. So this is Newton per meter, this is Newton. And I get my 20. I start drawing my free body diagram. I now have a little bit of an engineering sense. There is no Rx, because there is no force in the x direction. And the y must be going up and must be 40. And the moment reaction at the support is resisting this and this. So 20 by 7 is 140. 20 by 2 is 40, that's 180. And this is Newton, and this is Newton meter. Now, I'm intentionally not writing things because I want you to move a little bit and to start knowing things if they are easy. So I'm not going to say what is sigma fx, sigma fy, sigma moment. You need to start to have this sense of how the problem. First thing is, there is no force in x. So the support does not need to act in the x. It is ready to act and able to act, but it's not interested in acting because nothing has bothered it in the x. In the y, the forces going down are 40, then the support must go up by 40. And at the support, these forces are having a moment of 20 by 7, that's 140. 20 by 2, that is 40. According to me, that's 180. Going this way, well, this will go in the other way. Okay, so to our early Halloween, and oh, anybody in the back didn't get this? Okay, so we go this way. Okay. Good. Forces in 3D. Now let's assume that I have a force that's acting on a body in 3D. So I have a force in 3D, a rigid body in 3D that I want to study. And I have this force going there. Well, the force in 2D, we managed to find it to be F equal F cosine theta I plus F cosine, sine theta j. And this was our case here, a very simple scenario. This is F, this is theta. I could also write this in a different format if I want to be a little bit accurate. I could call this theta x, and I could call this theta y. So the angle that the force is making with the y, the angle that the force is making with the x. And this would be F cos theta x I plus F cos theta y j, and I guess you know it, plus F cos theta z k. So if I give you the value of the force and the three angles that this force is making with the three axes, just like that. Okay? Does this make sense? Because it's just intuitive. We have done this before. If you know this angle, it's the cos. If you know this angle, it's the cos. Okay? And if you remember, the very first problem in assignment 1, we said this is the force. And then we said, well, how about these axes? Well, you get this angle, and you get this angle. Okay? So if you know the angle between the force and an axis, the component of this force, the component of this vector, in the direction of this axis is just the cosine. Okay? And those of you who are very accurate will find that this is the dot product. Okay? So let's take an example. I have this as my coordinate system. This is my x, this is y, and this is z. Okay? And there is a force here that I want to represent. Can I have a pen, please? Or yeah, thank you. So there is a force here that I want to represent. Okay? Okay, let me see if I can put this way. Okay. So what I will do is that I will say, only if I can place this force in a plane with the z-axis. So this force was here. So I'll say, okay, can I find this plane where this force, it's still here, that is in a plane with the z-axis? Does this make sense? So my force becomes this. So the force is still there. I just made a plane between the force and the z-axis. Any problem? Okay, so let's see how would this look like. So I created this plane where this force is contained in with the z-axis. So this plane is built on these two lines, the force and the z-axis. Okay? And just for clarity, I'll say this line here is called h. Okay? So if you look at my example here, this is x, this is y, this is the force, and this is h. Okay? And so the next step that I will do is very simple. This is the plane that I created. This is z, and this is h. And this is my force. I can simply write that F equals, well, if I call this angle theta z, and this angle here theta h, then I can write that F equals F cos theta z in the direction of k, which is this. And this is called Fz. And I could also write that it will equal F cos theta h in the direction of h. And we did that in the very first problem of the first assignment. We had to name unit directions. So effectively what I did here is that I say this is the unit vector, and we agree to calling it k. And I also created a unit vector here, and we agreed to call it h. And this force here has an h component that's called fh, which is basically the force multiplied by cosine of this angle. Okay? Any problem? It is whatever you want to have. I called it h, but let's agree to call it m. That's fine. Let's call it n, whatever we agree on, as long as it's not confusing. Yes?
Sorry, so in this case, we're only looking at 2 planes right now, or no, it's 3?
One plane. That's this plane here. So what I did here is basically this. I took this plane and put it here.
Okay.
So this plane has z. So I took this plane out, and I just took this way. Okay? But here's the trick. FH is in the xy plane, am I right? Okay, so I can draw this. So this is the x, this is the y, and this is fh. Okay? And if we call this angle here phi, then I can write that this force equal F cos theta zk, nothing changed, but I could resolve this into the x and y. So this force here is actually F cos theta h. Well, it has a component here, and this is I, and this is j. And this component here is none other than fx, and here none other than fy. So I'll say the component is the force F cos theta h cos phi I plus the force and this is the way I represent a force in 3D if I know the two angles, theta h and phi. So if you are given theta h and phi, that's fine. You are done. Okay? If you look back here, you could also note that there is really no need to know theta h, because you could replace this with and so if I give you theta z and phi, you know everything. Am I right?
For the second line for the Fy component, shouldn't not be sine phi?
Yes, sine phi. I'm sorry. I wrote theta here. I'm sorry. That's phi. You're right. Let's take an example. Let's do an example. So this electric pole, which is standing in the z-axis, is supported by two cables. One cable that has a force of 120 newtons, and the other has a force of 85 newtons, or kilonewton, it doesn't matter really. And the first cable, the 85, is making a 36 degrees with the z. The second is making, and the h component of this, or the h part of this first force, is making a 64 degree with the x. For the other, the cable is making 60 degree with the xy plane, and there is a 20 degree in the negative xy plane. Okay? So how can I represent these forces? Oh, it's very easy. Let's look at F1. Well, F1 will equal 85 cos 36. That's the easy part. So I take F1 and I say it's 85, and if this is z and this is h, this is 36. So that's the Fz. So I say K. But note one thing. This component is in the negative z. So it's going negative. Then the h component, it will be plus 85 sine 36 in the direction of h. So that means I have a value here. This is 85 sine 36. So if I draw the second plane, this is the very x, the very y, and this is FH, and this is 64. Then I can write that F1 equals minus 85 cos 36k plus 85 sine 36 cos 64I plus 85 sine 36 sine 64j. According to me, this gives you 22I plus 45j minus 69k. And to check on yourself, the best thing to do is to say 85 equal 22 squared plus 45 squared plus 69 squared. That would be your check on yourself. It's very simple. Just a double move, like 2D problem. Anybody remembers the fish harness thing? It's a 2D problem. Okay? It's not actually a 3D, 2D problem. Let's look at the 120. So the 120 is making 60 degrees with the xy plane. So it must be making 30 degrees with the z-axis. So I'll say F2 equal, keep it down, 120 cos 30 k, but this is going down, which is negative. And let's call this axis here M, and let's name the unit direction in it to be Q. So I'll say plus 120 sine 30 Q. And here's what my first plane looks like. This is M, this is Z, this is K, this is Q, and this is my force. And this angle here is 30. Yes?
I think the Q unit vector is on x-axis.
Yes. It should be here. You are right. And so then I'll take this and draw the x and the y. If I draw x and y in this direction, M is going where? Well, M is in the positive y and negative x, and making 20 with the y. So this is M. Which means that this is the 20. And so I can write this will equal 120 cos 30k plus 120 sine 30. That's f in the direction of m. And then this will be sine 20 in the negative x I. And will be plus 120 sine 30 cos 20 in the positive j. I simplify and I will get minus 21i plus 56j minus 104k. Now, because I know you are very good and extremely smart, you will go and study ahead of me. So tomorrow, the very first thing I'll say in the lecture, so what is special about z? If you know theta x and phi, can you do it? If you know theta y and a phi, can you do it? There is nothing special about z. I just took the force and the z-axis and a middle plane. I could have as well took the force and the y and middle plane, the force and the x and middle plane. Am I right? And so it would be h and z, or h and y, or h and x. Okay? So this will be my first thing that I will say next time. Don't worry too much about it. You will know it tonight.